So this section of your book starts off with some things that I hope that you're quite comfortable with, and we won't be reviewing too much in class. Transformations of functions, so shifting up and down, vertical stretching and shrinking, etc. Symmetry of functions, whether function is even or odd or neither. And composing two functions we actually already have reviewed. Okay, so moving on to thinking about the exponential, which we've also already reviewed. Today we're going to talk about how to undo the exponential function, or more precisely, we want to be able to think about the inverse of the exponential function. So first we're going to do one quick example, how to algebraically find the inverse of a given function. So anybody remember how to find an inverse of any function? Switch the x and the y. So first I'm going to write this as y equals x over x plus 1. So instead of f of x, I use a y. Then swap out x's for y's and y's for x's. And then I want to solve this thing for y. So let's see. Just going to do some algebra here. I've got xy plus x equals y. Just multiplied both sides by y plus 1. Now I'm going to gather any term that has a y in it on one side and any non-y terms on the other. So I'm going to subtract y from both sides. And subtract x from both sides. So ideas now. Factor out the y. Yeah. So this says y times x minus 1 equals negative x. And then to get finally to get the y by itself, divide both sides by x minus 1, and you get y equals negative x over x minus 1. So that would be which of these formulas? C, yeah. So one way that we need to be able to recognize that those are the same. So I have negative x over x plus 1. When you have a fraction that has a negative sign somewhere, you can put it in the numerator or the denominator or like out front of the fraction. So I'm going to put it in the denominator. So this is negative x plus 1. So this says x over negative x. Oops, hang on. Is that a minus in my original? Yeah. This is minus 1. So this is negative x plus 1, which is 1 minus x. Okay, good. So again, to review, do you remember what these statements mean? What does it mean that y equals log base b to the x? Yep. An equivalent statement to this one would be that b to the y equals x. How about y equals log of x? Ten to the y equals x, yeah. And y equals ln x? Yeah, e to the y equals x. Okay, so logs are exponents, right? Log base b of x, that's the exponent that you raise b to make an x. So if I wanted to guess log of 800, trying to come up with a guess of what that equals, right? Then you're trying to come up with what power should I raise 10 to get an 800. So where does it have to be? Give me a range of values that it's between. Between 2 and 3, yeah, because 10 squared is 100 and 10 cubed is 1,000. So it's got to be between 2 and 3 and probably closer to 3 because 800 is closer to 1,000 than to 100. So I'm going to say between 2 and 3. Closer to 3. Then we can have our calculator get a more exact value for us, though it would still be an estimation, right? It still is going to be rounded because log of 800 is actually irrational. Log 800, 2.9 approximately. And then I want to write this as an equation, as an exponential equation. Log of 800 is approximately 2.9. How would I rewrite that as an exponential equation? Yeah, that says 10 to 2.9 is approximately 800. What is the relationship between e to the x and ln x? They're inverses. They undo each other. Okay. And what's the relationship between the graphs of two functions that are inverses of each other? Yeah, they reflect about the line y equals x. So if I draw that line in, then I can reflect over this line, and you can either eyeball it, right, or you can change points, right? So you swap the x and the y coordinates, right? Because that's what inverse functions do. X's become y's and y's become x's. So this point here on the y-axis at 0, 1 would become 1, 0. And negative 1, 1 would become 1, negative 1. And here this negative 3, 0 would become 0, negative 3. And this point negative 4, negative 3 would become negative 3, negative 4. And we're starting to get a picture of the reflection. So I plotted all the given points there. I have an extra one. What happened? Negative 1, 1 should become 1, negative 1. Oh, it's not actually 1, 0. That's like 0, comma 1 point something. So that would be 1 point something, comma 0. Okay, so these kind of curve from, oh, and then this one is at 1, comma 2, 2, comma 1 then would be on my graph. Okay, so there's my reflection for the right half, and then this is going to be kind of a little bit of a curve like that, and then like that. Okay, so if I want to sketch e to the x and ln x on the same axes, we could use our calculator, make a little table of values. I definitely know e to the x is going to go through 0, 1, because anything to the 0 is 1. And then I know it goes like this. I'm not being super careful about how this looks. Right. So that's my e to the x. And then ln x would be a reflection of this guy over the line y equals x. So if I put that in, help me draw the inverse. It would definitely go through 1, 0 for that 1 point, and then go down like that and up like that. Reflection over the line y equals x. So you should have a pretty good mental picture of ln of x as the inverse of e to the x. All right, so some basic properties of logs that you should be familiar with. If you want to take the log of a product, you can separate that into the sum of two logs. So log of a times b is log a plus log b. Log of a over b is log a minus log b. Log of a to the p is p times the log of a. Ln of e to the x is x because this is a composition of two inverse functions. They undo each other. And e to the ln of x, the same thing. This is a composition of two inverse functions. Inverse functions undo each other, so you get the x back. And there's no basic property for the ln of a plus b. So if you ever see that, you can't write that as log a plus log b. So having logarithms puts us in a position to be able to solve a new class of equations. Whenever the unknown is in the exponent, you can use a logarithm to solve it. So here my t is in the exponent, so I can solve this by using logarithms, but first I should isolate the exponential term. So I'm going to start by dividing both sides by 100. So we have 2 equals 1.01 to the 12t. So to get the exponent, to get the variable out of the exponent, I can take a log of both sides. And I can use any log I want. Usually we use the common log or the ln because we have that button on our calculator. Okay, but I can use any one I want. I tend to use ln. And the magical thing about taking the log of both sides of the equation is that when we can now use this property, where you can take that exponent and bring it down in front. So that is like a nice little trick to get variables out of exponents. Okay, so I've got the ln of 2 equals 12t times the ln of 1.01. And this might look complicated, but that's just a linear equation because the ln of 2 is just a number and the ln of 1.01 is just a number. So I can isolate t by dividing by those two numbers that are multiplied by it. I can say t is approximately equal to, well, I'll write down an exact. The exact value of t is the ln of 2 divided by 12 ln of 1.01. But I should get an approximate value. ln 1.01. And I get 5.8. So that's an important distinction. If you're ever asked to solve and find an exact value, you should leave the ln's in there. An approximate value you get by putting it into your calculator. So that's basically it for our review of inverses and log functions. I'm going to ask you to spend, let's say, 15 minutes working on this activity in your groups, and then I will give you the quiz after that. And the answers to this are on the next page.